Hello everyone, welcome to Lecture 5. So, so far we have discussed various search algorithms. So, the search algorithms that we have discussed so far are BFS or called BEP, breadth first search, and another search algorithm that we have discussed is called DFS or depth first search. So, in let's continue our discussion on the DFS for a while, then we'll talk about what are the limitations of the DFS. Then we'll move to the different algorithms called DLS and IDS, which kind of how they solve the limitations of the DFS and their own limitations. Okay, so let's start with the DFS. So we talked about that DFS uses the stack frontier, and we saw that it is so. If you talk about the properties of the DFS, then we talk about that it was complete if m is finite, right? So this, what is this m? This m was the longest path which was possible in this state space graph. So it was more like is there any sequence of nodes which kind of goes till infinity, infinite nodes, and if there is such path exist in the state space, then our DFS might just choose that path and go over this path until over the infinite, because what DFS does, it just picks one path and keep following that path until it reaches the end of that path. So if we but unluckily if DFS chooses this path, then there is no returning back because it will just keep going into this infinite path. So even though there was this simple solution here, it could, since DFS just end up picking this path first, now it has to go over this entire path until it returns and then goes or explores the another path. So that was the main issue with the DFS, that it simply picks one path and then goes to that path until it reaches the end. And because of this, the completeness was kind of like violated because of m being infinite. So there are some such problems where m is infinite or too large. For these problems, the DFS doesn't really work. We can't use DFS to solve our problems. So DFS at the space complexity of b times n. So n time complexity b to the power. So only space complexity was much better since it was in a linear format compared to the BFS, which had the or b to the power b exponentially. So here is because of this space advantage, we want to use the DFS in this kind of scenarios also where m is infinite or too large, but we can't use because if DFS becomes unlucky and goes along the path which has infinite nodes, then it will never be able to return the solution. So this is one limitation of the DFS is it can only find solutions if m is small or finite. If m is large or infinite, then DFS might end up going to infinite path and never in solution. So this was the one of the biggest limitation of the DFS. So so how can we solve this? How can we like do some more, can we do some more modification in the DFS, or can we use somehow DFS with some argument augmentations and all this so that we are able to solve this problem of m being infinite? So let me draw a search tree where m is infinite and try to see how we can use this, how what kind of modification we can do into DFS to restrict its movements. So let's say you have the search tree and there is this initial state, then there are, let's suppose, three node only, so b is equal to 3. Okay, so this is, let's suppose this goes on. mm, so this is like this. So let's suppose what was the issue with BFS? So DFS, if it end up choosing this path, then it will go along this path only unless it reaches the infinite this node, right? इसके बाद यहाँ पे आने के बाद it will go to upper and then backtrack into this. So if this path is infinite nodes, then it will never be able to find solution. But let's suppose कि if we just simply say the solution was here only at level 3, this was level 0, level 1, right? Solution was at level 2 itself. So since solution was at level 2 itself, why do we need to go till this? Why can't we simply backtrack from here and then check these, if then go over there, check these, backtrack, go over there and check this, and solution will be found. So we'll use this same idea to, this is what, so since solution can be found on level 2 itself, so what if we do some kind of a, what if we put some limit on the depth till which our algorithm can search? So if we put limit, on the depth till which search algorithm can search. So if we do this, if we put a limit on the depth till the search algorithm can search, then we should be able to bound first and then explore the other path. So for example, यहाँ पे अगर मैं third तक, जैसे 2 तक limit put कर दूँ, तो what will happen? Algorithm will start here, it will explore this node, it will explore this node, and now इसके आगे के जो भी successors है, these will not be added into the frontier. So stack. So these will not be added in stack because we have pushed. तो जो भी इस लेवल के बाद वाले successors है उसको हम ऐड ही नहीं करेंगे. ऐड नहीं करेंगे तो will not get to explore these. So what will happen? Algorithm will simply say कि इसकी कोई successors नहीं है. This will be the leaf node. So it will return back. यहाँ से then it will go to other path. We will do same here. यहाँ से it will go to back कि यहाँ से we haven't found any solution. Now the algorithm will choose this one, this one, this one, this one. यहाँ से भी अगर कोई नहीं मिला तो it will go to the table, यहाँ से यहाँ तक, यहाँ से यहाँ तक, and like this. So if we put this limitation, then our algorithm is able to find the solution. So this is known as a DLS, or depth limited search. So it is in one line. If I have to describe this algorithm, run DFS with a depth limit L till we can search in search tree. So this is the entire algorithm. Okay, we are still running the DFS algorithm itself. So overall approach is still same. There is nothing which is out of ordinary other than DFS. We are running DFS with same frontier, stack frontier, and so on. But what I am doing, one extra thing is that I am passing another argument called a depth limit to the function. So what will happen? Just say for example L is equal to 3. So DFS will start from the root node which will have the level equal to 0. And तो initially frontier में क्या होगा? Root node होगा. Now root node will be removed from the frontier and जैसे remove होता है उसके 3 successors add हो सकते हैं. Right? Let's suppose कि there are 3 successors. So all the successors will be added into 3. So since these successors जो हमने generate किए, these are just one level below the L0, so they will be called level 1. Right? Now अब इनके जो भी successors होंगे, they will be called level 2. So this will be level 2. So since we still haven't traced the depth limit, we can search still again. So let's create the numbers of these. So this will be the level 3. And जैसे यहाँ पे level 3 पे पहुंचे हम, जैसे level 3 का कोई नोड है, इसके कुछ आगे successors होंगे, but will not add any successors to this stack frontier. And because we are not adding any neighbors, our algorithm will simply explore nodes till here only, and that's it. And अगर इनमें solution मिला तो we'll return the solution. Otherwise we'll say that कि this is not solution or no solution found for the depth limited search. So this is how DLS works. So simply you can think of it as a L equal to the limit, whatever limit you set, and just simply pass DLS initial state goal and L limit. And जैसे L hit होती है, we'll simply return the DFS की no solution is found. And अगर इससे पहले मिल जाती है, तो we'll return the solution. So this is how DLS works. So if we talk about the properties of the DLS, if we talk about the properties of the DLS, then so we talk about 4 properties, right? Completeness, so then we talk about optimality, then we talk about time complexity, And then let's talk about space complex. So is it complete? So is DLS complete? So you must have be thinking ki what what happens if the goal is after this? Right? Let's suppose कि जैसे यहाँ पे level 3 तक success किया. But what if the goal was here? This was the goal node. This was just after the level 3. So will our algorithm will ever able to find it? No, it won't be able to find it because algorithm just terminated till level 3. So completeness is no because goal might be on lower levels compared compared to limit. So I D is greater than L. The depth of D क्या होता है डेप्थ ऑफ द shallowest goal node like the कौन सी लेवल पे हमें सबसे पहला गोल नोड मिल रहा है. So if the D is greater than L, then we'll never be able to find the answer. So this completeness is not guaranteed for DLS. So if completeness is not guaranteed, then optimality we can't even talk about because to find an optimal path, we need algorithm need to find the path first. So if it can't even find the path, how can it find the best path first? Right. So this optimality represents the concept of the best path. So since our algorithm can't find the path itself, how can it ever find the optimal path? So optimality is not is no for DLS as the completeness is also not true. So optimality can always be defined or optimality can only be defined after if the algorithm has the completeness. So if an algorithm doesn't have the completeness property, then optimality is by default it can't have. Right? It's not ऐसा तो कभी होगा नहीं कि एल्गोरिथम को पाथ नहीं मिल रहा लेकिन ऑप्टिमल पाथ मिल जाएगा. That doesn't even make sense because optimal path is also a path. So if algorithm can always find an optimal path, then that it means it is finding a path. So it should return true for the completeness itself. What's the time complexity? So since we are all just running the DFS here, so what was the time complexity of the DFS? For DFS, time complexity was big of b to the power n. So this was for DFS. And space complexity was b times n. बट अगर मैं यहाँ पे बात करूँ तो यहाँ पे m की वैल्यू किससे रिप्लेस हो गई है l से. Right, m has been replaced by l because this is the depth we can go into the search tree. So time complexity of DLS will be b to the power l. Space complexity will be b times l as l has replaced m in DX. Okay, so this is the algorithm called DLS, and as you can see, it is not complete, it is not optimal. Time complexity is a form of b to the power l, and space complexity is of the form of b times l. So the main issue with DLS is keep what happens, how do we choose the height? How do we choose this appropriate limitation, or how do we choose this appropriate threshold or threshold value for L? Because if we choose it too high, then we will say that so, then the entire purpose of this threshold will become negligible because algorithm will find the solution on much higher level, much lower levels like which are closer to root. But since we have chosen this L too high or too large number, then algorithm will go down on a single path for the जितने L number of nodes 5,000, 2,000, etc. But if we choose L too low, then we show that कि अगर goal L की threshold से बाहर है, तो we can't even find, we won't be able to submit the assignment, or we won't be able to. But then, sorry, so if goal is greater than, if goal is here at the, which is greater than the limit, then we won't be able to find this goal, because what will happen? Algorithm will just terminate here. So these were some properties of it. So how do we find this optimal value of the L? So that's where another algorithm that comes to our rescue is IDS, or iterative deepening search. So how does IDS work? I, so IDS is just simply an extension of the DLS. So instead of like fixing a threshold value for L, what we do, we'll keep moving the value for L. So we'll keep changing that. So we'll start with from L equal to 0. We'll check whether we have found the solution or not. If solution found, we'll return the solution. Right. Otherwise, we'll simply check for L equal to 1. Again, if goal is found, then return solution. Okay. If goal is found, then return solution. Otherwise, L equal to 2 पे जाएंगे. If goal is found, return the solution. Otherwise, we'll explore L equal to 3, and so on until infinity. So there will come a time like this. There will come time like L equal to D, which is the depth of shallowest node, where we'll find our solution. So this will be kind of like a terminating step for. But then what is this L equal to infinity? This L equal to is infinity if no goal node is there. Is there, and it's infinite state space. Then we might have to keep increasing L till the infinite to looking for the solution, but we will never be able to find it. So this is our IDS search algorithm. We'll start with the L equal to 0, and we'll call the DLS search with the start and L. अगर गोल मिलता है इसे तो we'll return the solution. अगर नहीं मिलता है तो we'll again run the DLS equal to L equal to DLS on L equal to 1, and so this is how the iterative deepening search algorithm works. So if we talk about the iterative deepening search in a more detail, let's solve an example of this. So let's go over our example. Let's start with the initial state. And this is our goal state. So we are talking about IDS. So IDS क्या करेगा? What's the pseudo code for IDS? If I just write the pseudo code, So for IDS, you can think of pseudocode as a for L equal to 1 to infinity, just call the DLS start and L. And जैसे solution मिला, just return, otherwise keep continuing this. So let's start with L equal to 1, level 1 of level 0 से we can start since we are given the level 0. So if we start L equal to 0, what will happen? We will search for only one level of the search tree, right? So level 0 क्या था? This itself, the root itself. So this was level 0. So root क्या था हमारा? The initial state. So for L equal to 0, if I maintain the frontier, this is my frontier and this is my visited set. And this is frontier. Frontier कहता है पे state. Okay. So what will happen? Frontier will contain the state A. We'll simply check whether we'll remove the A, check whether it's a goal node or not a goal node. So we'll simply mark it visited. And जो भी A के successors है, तो A के successors क्या हुए? There are no successors of the A which has the level 0, right? Because A के जो भी successors होंगे, जो भी ये A है, उसके successors जो भी हैं, these S, T, and Z, these are on level 1. So these can't be added because we are only searching for the level 0. So at this time, our frontier will become empty, and will return no solution found. Then we'll start with L equal to 1. Right, we keep increasing L1 by 1 until we found the solution. So again, we'll start with frontier, stack, visited. So we'll again start A being in the frontier because now we'll यहाँ पे फिर से DFS starting से start होगा DL, right? So what will happen now? We'll remove A, removed A, mark it as visited, and A के जो भी successors है, what are the successors of A? S, T, and Z. So let's add all these. S, T, Z. Okay. So if we just do this, now we simply remove Z, and Z के जो भी successors हैं, तो Z के successors क्या होंगे? O, but this will be on level 2, not level 1, so it won't be added, right? So we'll simply mark Z as a visited. That's it. We'll again remove T. T के भी जो भी successors होंगे, T के successors होंगे कौन से? L. It will again in the level 2, right? So these can't be added either. And similarly, S के जो भी successors होंगे, तो S के कौन से successors है? O, F, R. These three will not also be added into the frontier because now the level for this level is value is 2 and we are only searching for level equal to 1. So we won't be able to add these into the frontier. And since now the stack is empty, frontier is empty, you can simply return no solution found. Okay, now we'll start with L equal to 2. We'll keep continuing doing this until we find the solution for this. Okay, so now L equal to 2 के लिए क्या करते हैं? Again, let's draw our stack a little bigger this time. Stack, and let's draw our visitor set. So we'll start with A, remove A from the frontier, add it to the visitor set, and draw with A. Since A के जो भी successors है, those are S, T, and Z. They will be added into the frontier. So S, T, Z, remove Z from the frontier, mark it visited, and Z के जो भी successors है, let's add them into the frontier. Z के क्या क्या successors है? If we talk about Z के successors, so Z has only O, which is not in the frontier or in the explored set, so we'll add O into the frontier. Okay, now what we'll do, we'll again remove one node from the top, remove O. अगर मैंने O को remove किया तो क्या होगा? O will be marked visited, and O के जो भी successors है will be added into the frontier or stack. तो O का कौन सा successor है? S, which is already in the stack, so it won't be added anything anymore. So that's all for the O. Now we'll again remove one node from the frontier, which is T, mark it visited, and add it to the this node से explore word T के ऐसे. तो this is T. T के कौन कौन से successors है? T has only one successor, which is not in the one, which is L. So let's add L into the frontier. Now what? Again remove L, mark it visited, and L किससे explore word T से. So this was the level 0, this was level 2, this was level 1, this was level 2. So now L के जो भी successors है, L के कौन से successors है? M. Will this be added? No, because L के जो भी successors है, they will be of the level 3. So they won't be added back into the stack because we are only searching till level 2. So यहाँ पे threshold की value क्या है? 2. So L के successors want to be added. So now we'll again remove S. So let's add into the visited set. And S किससे explore होता है? A से. S के कौन कौन से neighbors है? S has two neighbors, F and R. So since it will add F and R into the stack, let's again remove R, mark it visited. हम लेकिन R के जो भी successors है, तो R के successors क्या है? P and C, but now this won't be get added because R के जो भी successors है, they will come to the level 3. This will be level 3, which is not allowed to search. तो R कोई भी successors added नहीं होंगे. Now what we'll do? Again we'll remove one node from the frontier F, add it to the frontier. ठीक है? Add it to the visitor set F, and F किससे explore हुआ है? S के थ्रू, तो we'll add F and A, and since F के जो भी successors है, F has one successor B, which is the goal node, but since it is still on the level 3, we won't be able to add it. So now that the frontier is empty, we can simply say if no solution has been found till level 2. So let's start for one more level. So let's start equal to L equal to 3. So let me again start with the frontier. This is my frontier, and this is my visitor set. This is frontier. And let's draw the search. So we'll again start with A into frontier. Again remove A, add A to the visitor set, and A के जो भी successors हैं, add those into the which is to S, T, Z has been added. Z has been added. Remove Z, add Z to the visitor set. And Z के जो भी neighbors है, तो Z की कौन सी neighbors है? O, तो add O into the frontier. O, this is level 0, level 1. O, now what we'll do? Again remove O, mark it visitor, and O के जो भी successors है, तो O के कौन सा successor है? S, which is already in the stack, so we'll not add anything on the A. So on for O, now what we'll do? Again remove T, mark it visitor, ठीक है? तो into T, mark it visitor, and T के जो भी successors है, T के कौन सा successors है? L, so add L to the frontier, remove L. If I remove L, add it to the frontier, and T के through हुआ है तो this is L, and this is level 2, and L के successors क्या क्या है? L के successors है M. Now we can add, because जो L के successors आएंगे, that will be on level 3, so we can add, since we are searching till level 3, so we can add M into the frontier, and we'll simply remove M, mark it visited, and add it to the frontier, and M के जो भी successors है, M के successors कौन कौन से? M has only one successor D. Now M के successors जो भी होंगे, they will be on the level 4, so these can't be added anymore. So M के लिए will not add any successor. What we'll do now? We'll remove the available node in different stack S, mark it visited, and add all the neighbors of the S. So add S into the first tree, and S के जो भी neighbors है, we'll add those into the frontier. So S के neighbors क्या क्या है? F and R. So let's add those into the frontier. F, R. Again repeat the process. Remove R from the frontier, add it to the visited set, and R के जो भी neighbors है, we'll add those into the frontier, because R के जो भी neighbors होंगे वो अभी भी level 3 पे होंगे, तो we are allowed to do this. R के जो भी neighbors कैसे है? P and C. So let's add those to the frontier. So C, let's remove C, mark it visited. So and C के जो भी neighbors है, C के neighbors क्या क्या है? C के neighbor there is P and there is D, which are already in the, so C के neighbors जो भी है, तो P है, and DA. But the CK neighbors, those will be on level 4, so these can't be added. Same goes for, right? So what we'll do, again we'll remove another node from the frontier, P, let's remove P, market visited, and P के जो भी neighbors है, they again will be on the level 4, so we'll not add them into the frontier. Now we'll again remove one node, F, market visited, and F, F is on level 3, so F is on level 2 itself, right? So if, this has become kind of mess. So this is level 0, this is level 1, this is level 2, and this is level 3. So F, F के जो भी successors है, F के successors क्या क्या है? Only there is only one successor, B will add that to the frontier. So B will be added to the frontier. Now what? Let's remove B. And we see that B is the goal node. So B is the goal node which has been found through F, and so we'll simply, since this is the goal node, we'll simply node, so we'll simply return the solution. Okay, so what's the solution here? The solution here is A to S, S to F, F to B. So this is the solution here. Okay, so this is how the IDS works. So if we talk about the properties of the IDS, let's talk about one simple property, completeness. So is it complete? Is IDS complete? Well, yes, it is complete, because since we are trying to increase the threshold one by one, so we'll reach the threshold as, like, even if the goal is too far, we will eventually reach, right? So we'll eventually increase the threshold so much that we will be able to find the solution. So yes, it is complete. What about optimal? Well, so now you see that the optimal is a little tricky here, but we claim that the IDS is optimal just like DFS. Optimal like BFS. Optimal like BFS. BFS क्या करती है? BFS is optimal as long as there is the path जो है, path की cost कुछ भी नहीं है, like there is uniform cost. So only optimal with uniform cost. Okay, so this is, so BFS, so our IDS is optimal just like the BFS. So it is optimal when the cost of the edges or cost of the actions are uniform. Why? So because since this is searching level by level, it will find the solution which is on the lowest level, right? Because एक अगर हम threshold को एक बार increase कर रहे हैं, so you can, if I give you a brief overview of this, like this. Let's suppose this is our search space, and we have two goal nodes. There is one goal node here and one goal node here. तो क्या होगा? Our IDS will first search for this level 0 cell, right? सिर्फ इतने nodes को search करेगी पहले. Then it will search for level 1. So now it will search for these many nodes. तो जैसे इसको ये मिला, it will return the solution, and terminate the algorithm. So it will always find this path to the goal, not this longer path. So this is just like a BFS works. So it is an optimal like BFS. What's the time complexity? Now this is a good. How much time this algorithm takes? So let's cover our example. Our previous example. You realize कि लेवल 0 पे ए विजिट हुआ सिर्फ, लेवल 1 पे ए फिर से विजिट हुआ और जेड टी एस विजिट हुए एक बार. एंड अब मैं यहाँ पे बात करूँ लेवल 2 पे, तो ए फिर से विजिट हुआ, जेड टी एस भी विजिट हुए और उसके साथ अलग अलग नोड्स विजिट हो रहे. एंड लेवल 3 पे भी ए विजिट हुआ, जेड टी एस फिर से विजिट हुआ, उसके साथ साथ जो लेवल 2 में विजिट हुए थे वो भी विजिट हो रहे. देन सम नोड्स. तो हो क्या रहा है कि जो लेवल 0 पे नोड्स है वो हर इटरेशन में विजिट हो रहा है, राइट. एंड लेवल 1 पे जो नोड्स है, जो बी नोड्स है लेवल 1 पे, those are being visited लेवल 0 वाले से एक कम पे, राइट. तो अगर मैं ऐसे कर करके दिस इज लेवल 3, सो लेवल 2, एंड अगर मुझे सॉल्यूशन जो मिल रहा है this solution I am finding is L equal to D, तो यहाँ वाले नोड्स ये कितनी बार एक्सप्लोर हो रहे हैं? ओनली वन टाइम्स. कुछ ऐसे सॉल्यूशन मिला, दैट्स. बट इससे पहले वाले नोड्स ये कितनी बार एक्सप्लोर हो रहे हैं? 2 टाइम्स. इनसे ऊपर वाले होंगे 3 टाइम्स. एंड सिम तो जैसे तो ये कितने टाइम्स होगा? दिस विल बी डी टाइम्स, क्योंकि डी इटरेशन हमें करने पड़ेंगे, राइट. एल इक्वल टू डी है तो डी टेक्निकली डी प्लस वन इटरेशन हमें करने पड़ेंगे. तो then this will be implemented d minus 1 time, right. So this will be for d plus 1 times, this will be d, this will be d minus 1 and so on. तो व्हाट्स द टाइम कॉम्प्लेक्सिटी ओवरऑल कितनी बार जनरेट हो रहे हैं? इस टाइम कॉम्प्लेक्सिटी हम किस में निकालते हैं? टोटल नंबर ऑफ नोड्स. तो टोटल नंबर ऑफ नोड्स कितनी बार हो रहे हैं? d प्लस 1 टाइम्स 1, बिकॉज एक नोड कितनी बार हो रहा है. तो यहाँ पे कितने नोड थे? एक. यहाँ पे कितने नोड है? b. यहाँ पे कितने नोड है? बी स्क्वायर. यहाँ पे कितने नोड है? बी टू द पावर डी. यहाँ पे कितने? बी टू द पावर डी माइनस 1. सो डी टाइम्स बी प्लस डी माइनस 1 टाइम्स बी स्क्वायर, तो 2 टाइम्स बी टू द पावर डी माइनस 1 and 1 times b to the power d. So this is the total number of nodes generated by IDS. This is the exact number of nodes generated by the IDS. So अगर मैं इसको big O notation में लिखता हूँ तो this will still be b to the power d, because since this term will be dominating term. ठीक है. So this will be the time complexity for IDS. So and there is this very popular question कि IDS versus BFS. Since both have the time complexity b to the power d, exactly number of nodes generate ज़्यादा कौन करता है? तो technically IDS does generate more number of nodes compared to BFS, but so नंबर है और जो डिफरेंस है दोनों में, दैट इज नॉट टू मच, नॉट दैट मच डिफरेंस, बिकॉज बीएफएस कितने नोट्स जनरेट करेगा? 1 + b² b + b² plus right, b³ plus b⁴ d. This is also b⁴ d. So this is the BFS wala and this is the IDS wala. So technically, yes, IDS does generate the more number of nodes compared to BFS, but if you fix some values of like b equal to 10 and b equal to 8, and if you calculate these values, you'll realize that the difference between BFS and IDS nodes is not that much. You can exactly calculate कि कितना आ रहा है and you will realize कि ये बहुत छोटा number है, इतना बड़ा भी नहीं है. Okay, so this, and similarly if we talk about the space complexity, स्पेस कॉम्प्लेक्सिटी किस पे डिपेंड करेगी, किस कौन सी एल्गोरिथम में रन कर रहे हैं यहाँ पे, सिंस वी आर रनिंग द डीएफएस इटसेल्फ, तो स्पेस कॉम्प्लेक्सिटी विल बी सिंपली 3 and that's it. So these are the properties of the IDS. So if you see, the time complexity is like a BFS, optimality is like also BFS, and space complexity is like a DFS. So our IDS, so IDS combines the features of both DFS and BFS. So it's like a best of both. So IDS is just a best of both BFS and DFS. So whenever we have a, we wanted to find a path on the uniform cost state space, we kind of prefers the IDS over the BFS, and we can prefer the IDS over BFS and DFS since it is kind of giving us the both best of both worlds. Okay, so with this, let's stop here and we'll continue in the next lecture. So in next lecture, we'll talk about another search algorithm called Uniform Cost Search or UCS, which will now, since we so far that we have talked about all the algorithms, these algorithm doesn't worry about the cost, like कि individual action की क्या cost है. They all treat all the actions similar. But now this is not the case always, right? Because some actions might have the different costs. So for example, if जैसे यहाँ पे आर से सीबीयू जाने की अलग कॉस्ट है, जेड जाने की अलग कॉस्ट है और टी जाने की अलग कॉस्ट है. So when will we? So we'll talk about another algorithm which will consider these costs in find or in taking the correct decision or finding the shortest or optimal path. So we'll cover that in the next lecture.